Hello everyone and welcome back to Solid State Physics in a Nutshell, brought to you by the Physics Department at the Colorado School of Mines. My name's Eric.
And I'm Nicole.
Today's video is motivated by experiment for those more applied folks out there. Back when the heat capacity of metals was first measured, the results were quite a bit lower than what was expected. So the question today is, why is the electronic heat capacity of metals so low?
So our goal today is to develop an expression for the heat capacity of an electron gas, first through a simpler approach that encompasses the physics, but not as precise, and then confirm our model through a more mathematically robust approach.
Recall from last time, the density of electrons can be determined by the integral of the density of states times the Fermi-Dirac distribution. So if we plot this versus energy at 0 Kelvin, we get filled states up until some maximum energy.
But as we increase the temperature, we saw last time that the Fermi-Dirac curve smears out, and electrons get thermally excited into higher energy states. And to first order, we can estimate the width as 2 kBt on either side of E Fermi.
So what does this mean for the electrons at really low energies?
Well, those electrons won't have the opportunity to get excited up to the Fermi level.
And what do you think that implies about the heat capacity?
That probably not all of our electrons are going to be able to contribute.
Okay, let's start with a ridiculously simple approach to determine the fraction of electrons that contribute to the heat capacity. If we have an n-electron system, we can invoke that there's an area described by this rectangle that contains electrons that can be excited thermally. This area is a fraction of our total electrons, roughly approximated by this rectangle. The ratio of these two areas is useful for figuring out how the electronic energy of the system changes with temperature. We can describe the temperature-dependent component of electronic energy as the subset of electrons that can be activated thermally, given by n times this fraction, times the energy associated with the thermal activation, kBt. The final thing to consider is the Fermi energy. We tend to rewrite this in terms of a Fermi temperature, so the units will ultimately be nicer.
Then to get the heat capacity, we just take the derivative with respect to temperature, and replace the Fermi energy with the equivalent temperature. Now people may be wondering how hot this Fermi temperature is. Typically, our Fermi energy is somewhere around 5 to 8 electron volts for a metal, which puts our Fermi temperature in the 70,000 K range.
Classically, we would have expected every electron to contribute with a fixed heat capacity of 3 kb per electron. Instead, we obtain this linear temperature dependence, which agrees really well with experiment. Back in the day, such agreement helped validate quantum mechanical models concerning the electron as a fermion.
At least speaking for the physicists in the room, taking areas of rectangles isn't that good of a mathematical model, even if it does work. Turns out we can get really similar results through some heavier math.
So we want to start with our system energy, which we build by multiplying the energy at a given mode by the density of states and by the Fermi-Dirac distribution, and then we take the integral over all energies.
Now if we look at our expression for the Fermi-Dirac distribution, we see these E minus E Fermi terms, and so we want to get an E minus E Fermi term in the integral so we can simplify it later.
So here's an easy way to get the E minus EF term. Recall we had an expression for the density of electrons as the integral over the density of states times the Fermi-Dirac distribution. We want to multiply this by the Fermi energy and take the derivative with respect to temperature. Since this expression equals 0, we can subtract this from our heat capacity equation. We can approximate that the density of states is relatively constant in energy at the Fermi level, so we can pull that out of the integral. Now we can rewrite the integral in terms of the variable x. After letting Mathematica handle the integral, we get an expression for heat capacity that is a linear temperature dependence.
So approximating the fraction of contributing electrons using rectangles wasn't really a bad approximation after all.
Now that we've got this background established, let's take a look at why we might care about this experimentally today. We can write our total heat capacity as the electronic part, gamma, times T, plus the phonon part, beta, times T cubed. At low enough energies, the electronic contribution starts to matter more than the phonon contribution.
And when you say low temp, how low do you mean?
Think in the 5 Kelvin range. Typically, to look at the heat capacity at such low temperatures, we plot the heat capacity as C over T versus t squared, so the slope of the line is beta, and the offset from the origin is gamma. And from gamma, we can calculate the density of states at the Fermi energy for metals.
Okay, so it looks like it's a good time for a quick recap. Today we developed an expression for heat capacity that depends linearly on temperature for all temperature regions. And we got this expression from assuming only a fraction of the total electrons contributed based off the Fermi Dirac distribution.
And finally, we took a look at how you'd use this model experimentally and found that it can give you insight into the electronic density of states at the Fermi level. Thanks for watching today's Solid State Physics in a Nutshell. Next time we're going to take a look at how well the particle in a box model describes solids through screening. See you then.